Welcome to section 5, optimal model selection. This is lecture 18, threshold optimization using the total cost of fraud. So if we take our XGBoost classifier and we follow the same approach where we've explicitly only selected the class probability of the fraudulent class and use that as our Y-pred, we can go ahead and follow a similar approach to thresholding using the AUPRC score. Instead, in this case, we're going to substitute that and we're actually going to calculate the total cost of fraud. So like we did previously, I've hard-coded the costs for each of the different classifications from the confusion matrix. These can obviously change depending on the context and the organization. I've just selected these values at random. Maybe they make sense, maybe they don't to you, but that's up to you to change. And then I've also created a list, an empty list for the total cost of fraud, the overall cost, with the intention of appending the scores to it as we iterate through the different thresholds, right? Then we simulate the same number of thresholds, so 100 of them between 0 and 1, and those are linearly spaced apart. We do the same classification update, where we update the classification based on where the probability is in relation to the different thresholds that we iterate through. Then we append those to the threshold list. Then what we do is we calculate the total cost of fraud in the same way that we did previously, where we generate the confusion matrix for each of the different classifications. We extract the individual quadrants, so the different classifications, whether it's a false positive or a true positive, etc., and then multiply the cost associated with that classification or misclassification. Sum those together and then append that to the total cost of fraud list, right? And then from there, we follow the same approach where we build a data frame and we plot the thresholds using Matplotlib. So the scale is quite extreme between some of the highest values and the lowest values. But really what we can tell from this is that setting the classification threshold very low or very high typically results in a very large cost. It's not optimal to do that. They do seem like outliers in the sense we could likely ignore this one. But even kind of within this range, even though the magnitude of the scale is a bit off, there is some deviation within this range, and we can explore that if we look at the data in the underlying data frame. So what we know is that if the threshold is 0, then we essentially saying that everything is fraud, and we're going to end up with lots of false positives, which each carry a cost of $10 according to the model that I've set up. Then if we set the classification threshold at the other extreme, where it's 1, and therefore everything is non-fraudulent, quite a few missed cases of fraud are going to creep through. And each of those costs $100 each according to the numbers that I've hard-coded. So therefore the optimal threshold for this model is around 50%. As we know, it's already quite well balanced, and that's according to a cost perspective as well. It's not identical to the metrics-based approach, but it's quite similar, right? And then we can see the total cost of fraud for each of the different classification thresholds. So this would be, $29,000, for example, where the extreme ends of the scale, if we set a very high or a very low threshold, then we're likely to see much higher total costs of fraud because of the misclassifications. Then next, what I'm going to do is I'm going to combine these predictions as well as the ground truth into a data frame, and then I'm going to save it to my local machine, because I'm going to use it in the next lesson where I'm going to build a fraud detection dashboard using Streamlit.